I welcome you all to the talk about enriching Solr with deep learning for question answering systems. I am Sanket Shahane. I work as a data scientist at Lucidworks. And Sawa is my co-presenter, but unfortunately he cannot be present here today because of his moving from Belarus to UK. And I encourage you all to connect via LinkedIn. And this is a joint effort by the data science and engineering team. Chow, who is here, she's the head of the data science. And Sawa, Chow, and I work on the modeling and research part, and Jake and Andy from our team work on the engineering part, like plumbing things together and putting it inside Fusion. So today we are going to go through like what a question answering system is in general, and what are the use cases, and where can we apply these to. And then we'll look at some of the demo examples to get you really excited, like what can a question answering system do. And we'll also look at the architecture that we use, and then we'll deep dive into the model architectures that we use, the features that we use for generating them and getting good results out of it. So wouldn't it be really great that if you're looking for something and it's right in front of you, like it's presented to you as an answer for your question? So I mean, who wants to go through like 10 pages or even like an entire document when all you're looking for is just a small paragraph or even 1 or 2 words? So well, the good news is that we can attempt to do it. So with the recent advances in the GPUs and the computational power that we have, we are now able to train complex neural network architectures and leverage huge amounts of data that we are generating. So we all have been hearing about big data and huge, enormous amounts of data. Well, deep learning and the advances in GPU are able to leverage that. Additionally, transfer learning is a concept which has made it possible for us to use models that have been trained on enormous amounts of data by someone else to apply them to our own use cases. So really, for our own use cases, we don't need like millions or billions of data points. All you need is like a couple of thousand, like 20,000, 30,000, it's going to be really fine. So typically, there are 3 types of question answering systems. One is the information retrieval type. The second one is the semantic parser, which is based on translating natural languages into SQL queries, and then you go to a relational database and get your answers out of it. For example, what is the stock price of Apple? That kind of questions. And the third one is like purely knowledge-based, where you build a knowledge graph from the existing data that you have. It's like highly structured semantic parser knowledge graphs or ontology-based systems, where if you have a question, you just go to that node and extrapolate and get around and look at the relationships between different nodes and get your answers. So we will be focusing on the information retrieval-based question answering systems, and we'll look at the architecture, research, and the use cases for it. So as a baseline to set the expectations right, we'll have Solr that's going to return us a couple of documents, and a machine learning model or multiple models or ensembles that will do the re-ranking and give us a really good result on the top. So let's look at some of the use cases. Like before we go to the demo and talk about all the technical stuff, I mean, what are the business goals that we can solve, or what are the business expectations, or why should you even care about this stuff, and where would you apply this? So, well, businesses have customers, and we all care for our customers. So we want to give them the best possible experience when they're dealing with us, whether it's on our website, whether it's with our customer support channels, or anywhere where our name is associated with. So customer satisfaction, user experience, and of course, if you streamline your customer support, we want to earn more money. So that's what we can achieve. We want people to find the most relevant information to their query on our website, so they don't have to go through a painful process of contacting our support page and waiting for like hours or even like a couple of minutes. In the best case possible, you have a very streamlined support system where someone asks a question, a human replies back in a couple of minutes. Well, we should try to attempt and do that within seconds or even milliseconds. So what we would like to do is basically look at our historical data and try to answer the user's query as fast as possible. So that can be achieved through question-to-question similarity. That is basically FAQ matching, that when someone writes a question, for a single question, there are multiple ways you can frame it. So what we want to do is generalize and find similar questions to the ones that we have previously answered, or people have been asking us many times, and our support center has answered that. Then we would also like to give the user the direct answer that they're looking for, right? I mean, it's the best case scenario would be someone asks you a question and you directly give them an answer. If not, well, look at some of the questions. We think that you might be talking about some of these questions that we have already answered. So that's what we would like to show them. Also, the support center at the back end can use the same framework. Like there are like domain experts who are really good at understanding what the domain is and can answer questions related to their own domain. But when you go to scale out, you onboard a new person coming in, you need to train him a lot to be able to perform at the same efficiency level. So they can leverage this framework and kind of find out the answers that, oh, someone expert from our company has already answered, and how has he done it? Let's look at it and take advantage of it. So let's look at a demo how we can do it. So let me see. OK, so this is a demo we built out of insurance question answer pairs. So the input to our deep learning models was like a set of questions and the corresponding answers to it. So if you ask a question related to the insurance domain, we have some answers to it. So let's see, can my wife drive on my insurance? So well, even though I'm not married, but let's be prepared for it. So well, here is like, we have two different panels here. On the right side, we have the answers that out of, we have like a set of about 20 to 25,000 answers. And given this question, we are trying to find out the best possible answer related to this question. So you can see here it answers you like some of the coverage on a separate auto insurance policy. Well, yes, you can drive it. Every person in the household must be listed on the auto insurance policy. So another interesting thing is we can show what are the similar questions that people have been asking to us. Well, not exactly this one, but people ask about, does my spouse have to be on my auto insurance? So this is a question that our model has already seen. We have been asked this question before. And the way it can generalize well is if you look like wife and spouse are really interchangeable. And some people also ask like, can my girlfriend be on my insurance? Well, that's an applicable for me. So you can just directly show them the answer. Oh yeah, these are some of the things that this is closely related to what I was looking at. So you really like on the spot, you try to answer their question so they don't have to really go and ask the customer support center to you. Another example we can see is it compulsory to have home insurance? So well, this is again a really good example here. Like homeowner insurance is not mandatory for those who don't want to be covered by like damages to your home through fire, wind, and theft. So if you look at some of the similar questions here, it's like, is homeowners insurance compulsory? So it's like, is it mandatory to have homeowners insurance? So these are like interchangeable words that the model is able to understand. Is it a legal requirement to have homeowners insurance? And it also learns like double negatives. Like, is it illegal to not have homeowners insurance? And that's the level at which we can generalize it well. So I just had some backup slides in case live demo doesn't work. So yeah. And another data set that we worked with was we crawled a lot of email lists from Apache, like on different projects like Solr, Lucene, Spark, and like all the discussions that have been going on the user list and the developers list, and indexed it into Solr and tried to make our approaches and our architectures work on them. So I have a screenshot here where someone asks like a question like, does Lucene have backwards compatible API? Well, we are doing even a decent job on this part. This data set is like really hard, where people have been posting codes, their error logs and everything, and we are like digging through all of that and finding here that, well, Lucene 4x cannot read Lucene 2x, whereas Lucene 3x can read Lucene 2x. So one version backward compatibility is still supported. We have it on the second position, not on the first position, but that's just because the data is really hard to comprehend in this case. So we have another one here where what are the pros and cons of Lucene versus a database like MySQL and creating indexes on it? So we have the answer again on the second position here. It's the most obvious answer is that the full text indexing features of RDMS are not as good as Lucene. So these are like really relevant answers to what the user is looking for. So before we dive into the technical terms, like now you have seen the demo and what it can do, let's catch up on some of the basic terminology that we'll be using through the talk here. So what is supervised learning? It is literally what it says. You supervise the model's training, the machine learning algorithm's training, by providing it examples. In our case, it's going to be questions and answers. Dude, look at these questions and answers and learn the pattern and the hidden representation inside it and generalize on the new questions that I get. Unsupervised learning is where you yourself don't know what's the label of the data, like what is the right answer for this question, or what are the similar questions to the ones that have been previously asked. So you say, go ahead and just look at the data. This is all the data that I've got, and find out what are the patterns hidden in it. So deep learning are all the approaches where the neural networks are like at least more than 2 hidden layers deep. So all the deep neural networks are, we just say them as deep learning. And the traditional machine learning algorithms are, like when we talk about that, it's going to be random forest, XGBoost, logistic regression, the ones that are basically not deep learning based. And we have been experimenting with random forest and XGBoost, and we try to tune them using advanced algorithms like differential evolution. And we have always found that XGBoost always beats random forest when you tune them heavily. So let's look at the architecture. It's time about all the technical stuff here now. So why not just use Solr? So as we have seen, Solr is really good at finding text documents, like doing a keyword match. But here we need to go beyond just text matching or keyword matching. We need semantic information in it. So that's why we need to use machine learning here. Well, then why not just use machine learning all the time if it's so great? Well, the problem is it's not scalable. If it's about 20,000 documents, 30,000 documents, deep learning is going to work just fine, or any other machine learning model. But when you have to scale it up to millions of documents, you're going to hit performance issues. And it's going to take a longer time to return the results. And by longer time, I mean it's the user acceptable time on a website, which would be like at least a second, like 800 milliseconds to 1,000 milliseconds. So we want to do it before that. Otherwise, if someone has to wait for 20 seconds, it's not going to wait, probably. So why both? Well, Solr is really great at finding relevant documents out of millions of them, or even billions if you scale it properly. And machine learning is able to kind of give you high precision answers. So how do we use them both? Using an LTR style. So learning to rank style, where Solr returns some documents and then deep learning runs on top of it. So the deep learning or the machine learning models are going to look at the top n candidates that are returned by Solr. So the top n typically depends on how much time you can allow these machine learning models to run on. So typically about 100 to 1,000 documents is going to be really fine. So in this two-step architecture that we are using, we expect that Solr should return the best possible answer so that our machine learning models can score the best ones on the high. So we expect high recall from Solr and high precision from deep learning. So let's take a look at the indexing pipeline. So traditional machine learning models like XGBoost require a lot of feature engineering, and some of these features are really dependent on what the query is coming. So if the question changes, all the feature values are going to change. So for example, the cosine similarity between doc2vec vectors, or even the TF-IDF match between them. So if a question changes, that has to change. So the only option we are left with is to generate them on the fly. So when we're doing that, however, what we can do is on the answers that we already have, or the data that's going to reside in Solr, we can pre-compute some of these features. So so that's why we have two stages here, which is the NLP annotator stage and the word2vec stage before it goes into Solr. So we extract parts of speech, named entity recognition out of it, sentences in the documents that you have, and index them as overlapping tokens in Solr. Plus, we extract the word vectors for it and store them in Solr. So when we are doing query, the first stage is about query expansion, and this is a very domain-specific stage which contains like variety of options that you can do here, are like synonyms, expansion, or an answer type classifier. Like answer type classifier are like it's a supervised method where it learns to predict. Like when you ask a question, it will tell you whether it's looking for a person or an organization. Like for example, who is the president of United States? Well, you're looking for a person. So we have already indexed the NER in our answers, so you know like an answer should contain a person in it. So that kind of things. But these are really like domain specific. So if your domain changes, these might not be applicable. And that's the roadblock that we hit when we were using the Apache mailing list. Like no one's coming to Apache and asking who's the president of United States. So we came up with an unsupervised method based on mutual information. So what we try to do is find out associations between words that are asked, words or phrases that are asked in the question, and how they map to the answers, like which are mutually exclusive to each other. So for example, like question could contain keywords like indexing, type ahead, and autocomplete, while the answer has most of the times words like Solr and Lucene. So you can also use this as a correlation feature inside the XGBoost model like we are doing it right now, but the user is free to play with this part. Then we extract the entities like person names, organizations, and like parts of speech like verbs, nouns, etc. from the query itself. Then we get the word vectors for it so that we can compute the distance, like the word-to-vec distance between the question and the answers there. Then we go to Solr and use the LTR API to get the most of the features that we can get out of it, because Solr we are trying to push down most of the computation down to Solr, like number of overlapping tokens between the two questions or features like that. Then after Solr has returned most of the possible features, there could be some features like how many number of URLs are there in this answer, or how many question marks are there, and things like that, which are not going to be done by Solr. We have a JavaScript stage which does that. Finally, we have a re-ranking model, which looks at the top n documents from Solr, which is an XGBoost model in our case. So let's look at some of the stages in Fusion. So these are new stages in Fusion. The NLP annotator stage, which allows you to use OpenNLP or Spark NLP to extract the NER and POS out of it. Then we have the word-to-vec vectorization field stage, where it takes in the question and vectorizes it, and it will ask you to specify which field contains the pre-computed vectors, and use this to compute the cosine similarity between them. And then we have the learning to rank stage, where you upload your trained XGBoost model to the blob store, and then it uses it. So we also have a deep learning stage coming in, where you would train a Keras model or a TensorFlow model, save it in .h5 format, and then serve it at query time. So now that we are familiar with the architecture, let's look at some of the models that we developed. So let's start with the question-to-question similarity, or FAQ matching. So the use case is about finding similar questions or duplicate questions that our customers have already asked. So we experimented with different supervised models, unsupervised models, and ensembles, basically combining multiple models together to see which one performs the best. In total, we compared 38 models, but don't worry, we'll discuss only a few of them. The dataset that we used was Cora's duplicate question detection dataset. Basically, if two questions are duplicate, it is labeled as 1. If it's not, then it's 0. So let's look at what are some of the features that we did on the XGBoost modeling part. So first one is the standard TF-IDF cosine score between the question and the another second question that you're looking at. Then we look at the cosine score between only the nouns. Like you just discard everything, but just keep the nouns and check the cosine distance between them. Then you have number of question keywords that are overlapping. For example, how, where, when, how much. Like what's the overlap between these keywords? We have a big list of these keywords there. Then what are the number of overlapping parts of speech tags there? So basically, you could use a different adjective to use the same question, like frame the same question. But here it's going to see what's the overlap between the parts of speech there. And again, overlap between the NER tags there. On the unsupervised part, we use standard Solr and then TF-IDF, well, different variations of TF-IDF with sublinear term frequencies and n-grams instead of just tokens. And then we also use doc2vec, fast text, and GLUF and Google Sentence Encoder. These are basically pre-trained deep learning models that have been trained by Google or Facebook. Like FastText is released by Facebook a long time ago, and Google Sentence Encoder is like really a new one. And all these models are released by training them on like huge amounts of data. So when we are using them, we don't have to retrain them all again. So we can, in an unsupervised way, we can just look at our data and train them. Then we also do an ensembling of Solr and along with Google Sentence Encoder. So this is the feature importance that XGBoost gives. So it says that cosine is the best feature to look at, then the cosine nouns, and the parts of speech overlap. So that it tells us like different adjectives can be used to reframe the same question. So it's paying attention to that. And it's not paying so much attention to like how much is the NER overlap in it. So if you look at the model performance, we are looking at recall at 1. When we were doing our research, we also looked at recall at 3 and 5 to see like where does the model rank the answer. So you can see that XGBoost here does not perform like much better, like significantly better than using Solr out of the box, like without doing much work on it. Whereas if you look at Google sentence encoders, it's performing really good, like about 85% recall there. However, like if you put Google sentence encoder with XGBoost, like make an ensemble out of it, it's actually hurting Google sentence encoder. So then we have TF-IDF ngram. It's not significantly better than GSE, but it's still performing really good. Then we have a combination of TF-IDF or Solr. You can replace Solr with it, with Google sentence encoder, which gives us the maximum boost. You can achieve up to 91% at the recall part there. So the conclusion here is that it's unsupervised ensemble methods with TF-IDF and Google sentence encoder provide the best results with less amount of work. So you really don't have to worry about feature generation and all that trouble you have to do with the supervised data, like data curation and gathering all the data. The part about supervised learning is when you generate these features, when you know that, oh, this model works great, but same features might not be applicable to a different data set. So on an unsupervised method, it's really well to generalize because you're not generating domain-specific features. You're just using a method that can run on any kind of data there. So on single supervised models, like generalized TF-IDF with n-grams works really good, and the Google sentence encoder also is like good if you don't want to do an ensemble there. So XGBoost models do not have any big advantage over the unsupervised methods. Even you can go with Solr there. So let's take a look at answer selection. So the use case here is like given historic QA transactions, like from the support team archives, the Slack channels, or the Stack Overflow, or email threads that you might have, when a question is issued, we want to pick the best possible answer. So if you look at email threads that we did with Search Hub, someone asks a question, there are multiple follow-up questions to it, or someone just says, thank you, oh yeah, how does it work? I have the same question. But what we want to do is really find the one answer, the one reply that really answers the question. You want to re-rank it and put it on the top. So on the research part, we did like extensive feature engineering on the supervised models for XGBoost. We trained a deep learning supervised model, and we also looked at some of the unsupervised models there. So we compared total 21 models here, and the data that we ran was insurance question answer pairs that you have seen the demo before on. So the methods here are XGBoost and deep learning are based on supervised data, and we use FastX, Word2Vec, and Doc2Vec for the unsupervised part. So to quickly go over some of the features that are used in the XGBoost is, first is the same feature that we had. Cosine similarity between the question and the answer after trimming the stop words and standard tokenization. Cosine similarity between the TF-IDF vectors of question and answer after extracting nouns out of it. Then we have one-hot encoding of question keywords like who, when, what, how long, how much, and how fast. So we have one-hot encoding of POS, parts of speech for the questions and the answers, and the NERs there. Word-to-vec distance between the question and the answer. We combine unsupervised models with supervised model by using them as a feature inside XGBoost. So we also use Doc2Vec to find the cosine distance between the questions and the answers. So if you look at the feature importance plot that XGBoost gives you, is it pays the most attention to Doc2Vec vectors, Word2Vec, cosine, standard cosine distance followed by cosine among only the nouns. And then it says that, oh, NER is an important feature here, like NER called as organization. And if you look at the last part here, it's like it pays some attention to one of the keywords. Like this is the first keyword that it chose out of the list that we had provided. It says like how much. So when we went back and looked at some of the questions, it's about when someone asks about how much, they're typically looking for a quantity there. Like how much water should I put in something, like that kind of question. So that's an interesting find that we have here. So now let's take a look at the deep learning architecture that we used. So we used a triplet-based model where we provide a question, a correct answer, and an incorrect answer to the network and let it learn the deep representation of the data such that the cosine similarity between the question and the answer is maximized and the cosine between the question and the negative answer is minimized. So basically we want to just maximize the distance between these two answers. So for that purpose we used a shared encoder here for the questions and the answers. So some of the layers of the encoder here are like first when the question comes in, we pass it through an embeddings layer, and then we do a dropout on it. Dropout is just a concept used to avoid overfitting on it. Then we pass it through bidirectional LSTM layer, and then finally through an attention weighted average. So what attention layer does is basically it gives the model access to some of the previous tokens or the words that it has seen. So in the next slide, when you see a shared encoder, it's just going to be this entire layer, like 1, 2, 3, 4, 5, all these 5 layers. So here's what we do at training time. We take a question, a correct answer or a positive answer and a negative answer, and pass it through the same encoder. So the encoder here is this entire like stack of 5 layers here. And then we compute the cosine distance between the positive answer and the question, and same thing with the negative answer. Then we concatenate them, and our error function is to maximize the distance between these two. And then when we want to apply this, what we do is we just pick out this encoder layer here and pass all the questions through the encoder layer and generate a vector representation for all the questions. And whenever a new question comes in, we just pass it through the same encoder and map it in that vector space and do a k-nearest neighbor. Like, what are the nearest neighbors for this particular question that I have? So it picks up all the similar questions. When you saw the demo on the left pane, when you had similar questions, it's doing it like this, like doing a k-nearest neighbor in that vector space. On the answer side, what we do is the same thing. We just pass all the answers through the encoder into that vector space, and when the question comes in, we map it to that same vector space and see which are the answers closest to this representation here. And that's how we are able to generalize these things well. So if you have exact duplicate questions, then that's going to be ranked the first because it's going to exactly sit on top of that particular question. And when you look for more answers, like expand your search space, you're going to find more like when it does like wife and girlfriend and spouse, that kind of thing. So if you look at the model performance here, we look at the F1 score here. So we see that deep learning does really well here, like gives you about 85% on the F1 score. So we combine it with XGBoost and it's almost the same. But if you look at just XGBoost with Doc2Vec, it's not really the best model that we have. So we can say that when deep learning is fed into XGBoost, it's just leveraging XGBoost and showing us good performance there. So unsupervised methods, Doc2Vec was the best among all the ones that we tried, and it's still not really the best one that we have. So here, and another question that we are like always asked is, how much data should we use for a deep learning model? Like, how much is it really required? So what we did is we tried to see the stability of the models across like varying the training data sizes. So when you give 100% training data, which one performs the best versus when you give 50% and then reduce it like significantly to 10%. So I think our 10% is about 3,000 samples. So then you see that XGBoost is like really a stable model. Its performance doesn't really vary that much if you give like increase the data size or reduce the data size. Whereas if you look at deep learning, if you don't have enough amount of data, it's just performing barely as comparable to XGBoost there, which is just a traditional and simpler model to train. So the suggestion here would be like basically if you don't have enough amount of training data, just stick to XGBoost or traditional models there. And an interesting thing to note here is basically if you look at when the data is at 10% size, when you combine deep learning and XGBoost, it's actually holding up above what a deep learning would suffer from. So XGBoost is like kind of pushing, hey, you are suffering, but I'm here. Like I have some other features to get good performance out of here. So the conclusion here would be like deep learning models are significantly better than traditional models, except when you don't have enough training size. So, and there is a significant advantage of using supervised methods here over unsupervised methods. So if you go back to the chart, we have the best possible performance we could get out of unsupervised methods was 63% F1, whereas with the deep learning, we could reach up to 85. So the suggestion here is like if you have less than 5,000 samples, you should start with XGBoost, and you can give a try to deep learning, but it's not going to be that great. And another thing that I would like to talk about is deep learning is often regarded as like a black box, or it's like unexplainable, like thousands of parameters to train. We don't know why it's working or how it's working. But is it like really unexplainable? Well, not all of it. So we have different, like there are various open source projects and blog posts where they explain on a convolutional neural network where how is it learning the images, how is it deciphering each stage of the image, learning different features. So we have a sentiment analysis module coming up in Fusion, which is based off of deep learning, where you can see here it's powered by deep learning and it's able to explain itself. Like why did it choose a particular comment as positive sentiment or a negative sentiment? So here it says like there's a rebuild of poor quality and has like tons of problems in it. It's pretty much a rep and things like that. It's worthless. Whereas if it's a positive sentiment, it's focusing on I recommend this for anyone who has an iPhone 4. So We use attention-weighted mechanism here, where basically we are able to, the model is able to tell like which are the parts of the text where it's paying attention, and we leverage that to provide analysis to the user, like, hey, this is why this particular comment was tagged as negative or positive. So how you can use this is you can do entity extraction on top of this and tag a sentiment with an entity. For example, if it's about a particular product that you have, you can extract the product out of this and say, hey, when people are talking about product X, they're talking about the build quality of it, or what is it that people love about this. You can also do an aggregation on what are the keywords that people specify about it. You can look at what's the things that people love about our product. So these are all the use cases that you can do. So deep learning is not all that mysterious, so we are learning to decipher deep learning slowly. Well, that's all I have for the presentation, and we can open it up for Q&A. We have a couple of minutes left here. So Chow can also help you like answer some of the questions if you have here. Yep.
So in your deep learning model, were you using a convolutional technique, or was that just a recurrent model?
No, we are using a LSTM model, long short-term memory layers in that. It's not a convolutional layer. Yeah.
But it's not recurrent.
Well, it is a type of recurrent layer. LSTM is a type of recurrent layer, but it's not the convolution. I don't know if it's working.
Several like specific variation like GRU and LSTM. Here we're using bidirectional LSTM. It's like looking at data from left to right and also from right to left, so that you do not like, because like it's depending on the memory, it's a sequence time series model, and then if you're encoding everything at the last hidden state, it will forget what's in the front. So it's good to have bidirectional, then you don't lose the information at the front or at the end, and then you concatenate the two directions together. So, and then a lot of the Kaggle computation when you're using bidirectional LSTM.
Yeah.
That experiment you did with the Lucid mailing list, is that is the steps you took to do that? Is that, I know you didn't have great results with it, but is that on a GitHub somewhere? Can we reduce it? I think it would be really useful to the community if we could make that even better just over time.
Yeah, so it's still a work in progress, but it's not like published on GitHub yet. But once it's like at a level where we can publish it out, so we are still in data curation processes. Like we want more, the cleaner the data that we get, the better results that we can get out of it. So, yeah, sure. Yeah, that's a good idea actually to put it out there.
This is like Lucidworks have a search hub. GitHub is like that's the same repo, and then maybe next year sometime we'll release a version with the search hub. Search hub already have several machine learning models we publish there, and then maybe we can publish the QA part too.
Yep. Cool. Any other questions? So, and if no questions, then so one of the use cases that where you can curate like FAQs out of is like product descriptions. Like if you're an e-commerce website, right? Like people have like descriptions and people already have answered questions about a product in that. So you can get that data out of it. So you have like thousands of products, or even like some people have millions of products, like if it's a major e-commerce retail. So you can curate that data like about the product description and what are the questions asked about it, and use that as the training set. So next time someone comes in and asks a question about a product, you can directly attempt to answer that. So that's one interesting use case around that.
So this Q&A, when will be available in Fusion?
So I think, so we are basically building pipelines, like the pipelines that you saw, like different annotator stages. So I think by 4.2, we should have something that can be used on your data set. Yeah. So these are like, so the deep learning models, so on the sentiment analysis model, these are like, these models can be generalized well. Like we can train them on large amounts of data and can be transferred like on small amount of data you have. We can transfer that and fine tune them to work on your data set. But for a question answering system, the one that you saw in the demo, that's like you need at least like 5,000 examples. That would be really good to use that data.
The pipeline that you are shown with the different steps, with name entity recognition, part of speech tagging, and so forth, how long does it take to execute, to run on a single document?
So that is not really a bottleneck, but I don't have the benchmark results, like exact times for each of these stages. But we have like different options there. Like we used to use OpenNLP, which was kind of slow, so we have incorporated Spark NLP, which is much faster than OpenNLP. But I would say it's a slight overhead there, like doing word-to-vec and parts of speech.
How would you rank it? Is it between 0 and between 1 and 5 seconds, or 1 and 10 seconds?
No, it's not that long. It's going to be like in milliseconds. It's not, yeah. Yeah, I mean, it has to be in milliseconds. Otherwise, it's not really usable.
Yeah,
So.
another option to do in ER and QoS is like using the deep learning model. And Spark NLP give you the API. You can run deep learning model on your own data. And then we're also thinking about like shaping the pre-trained model for different QoS and ER tags.
Thank you.
Yep. So I think we have a break now here. So you guys can enjoy your coffee. Cool. Thanks.